So I'm going to continue with projectiles. The next section is called projections or projectiles at any angle. It's quite an odd title because effectively it's exactly the same as the previous section, rather than implying that you're doing an obtuse angle or anything like that, because that would just project it in the other direction. So I don't really know why it's called that. It should just be problem solving or something like that, but there we go. It's called projections at any angle, but it's just more of an problem solving type section. The only additional bits of information you need to know are if I have my projectile, because this is a parabola, I am able to work out the greatest height quite easily. Now, quite often you won't know this information, so whilst if you knew how long it would take to get a certain part, if you knew that distance, you know the maximum height would be in the middle, depending on the problem. It does depend on the problem. The main bit of information actually that you need to know is that at this point the vertical velocity is 0. Okay, so the vertical velocity, because at that point it changes direction. So to find the greatest height, we bear in mind the vertical velocity is 0. Other bits of information we need, if it asks for the time of flight, that is the whole time from when it is released up until the point it then lands again on the plane. And the horizontal displacement or distance is often called the range. Why it's called the range when we use range in a functions type format, I don't really know, but it is. So range, time of flight, and at the greatest height, vertical component of velocity is equal to 0. Likely to use that kind of thing in the SUVAT formulae. So there's 4 different examples because this section is quite a bit more complex. But hopefully by going through the problems you can see the kind of thing that you'll have to think about when you're approaching these problems. Okay, so example number 1. So a particle is projected from a point 0 on a horizontal plane with a speed of 28 meters per second with an angle of elevation of 30 degrees. So always sketching, always sketching. After projection, the particle moves freely under gravity until it strikes the plane at point A. Find the greatest height above the plane reached by P. Now, before we start any of these problems, we need to create our vertical and our horizontal component. So a horizontal component, if I'm resolving horizontally, is going to be 28 cos 30, which simplifies to 14 root 3. And my initial vertical velocity is going to be 28 sine 30, which is equal to 14. So the initial, if I put my units in, reminds us that this is the initial velocity, horizontally and vertically, 14 root 3 meters per second and 14 meters per second. Now we've got the information, we can approach the questions. So find the greatest height above the plane reached by P. So because we're talking about vertical height, then we do need to resolve vertically. So we are approaching these always as SUVAT problems. We have a constant acceleration, which is gravity, so we're always looking at it in terms of SUVAT. So I know my initial velocity. My initial velocity vertically is 14. My acceleration due to gravity is negative g. So it's negative g because I have defined upwards as positive. It makes sense that upwards would be positive because I am talking about it reaching this point. So the projectile, the particle is moving upwards, and then it means that this initial velocity, or this one here, can be positive as well, rather than thinking of it as negative. So what other information do I know? What do I need to find? So I need to find displacement. So that's what I'm working out. I know at this point the final velocity is 0 because it's about to change direction. So S, A, U and V means I'm going to use V squared equals U squared plus 2AS. So 0 is equal to 14 squared minus 2 lots of G, so 19.6 S. So 196 is equal to 19.6 S, because 14 squared is 196. So therefore, the maximum height reached by the projectile or the particle is 10 metres above the plane. So when you know what aspects it is you're finding, the actual problem itself isn't too challenging. Okay, part B, the time of flight of P. So that's the whole journey. Now, it might make sense, you might want to think to resolve horizontally, but we actually don't have enough information. Whilst we know the initial horizontal velocity, and we know that the acceleration is 0, we're trying to find time, but we don't know how far that is, and our final velocity is still 14 root 3. So the fact that we haven't actually got enough information changing means we actually can't solve the problem. When we've got 14 root 3 and 14 root 3, it ends up with t is equal to 0, so it doesn't find the whole time of the flight. What it actually finds is the initial time. So it's not very helpful in that situation because we don't have enough horizontal information. What we do know is a lot more about the vertical information. Now I've defined upwards as positive again, mostly because people are more likely to make the error of keeping that positive even if they define downwards as being positive. So I'm trying to avoid that error really. So resolving vertically, my initial vertical velocity is 14. My acceleration is negative g, because it's going in the opposite direction. I don't know my final velocity, so I can't use that. I do know, though, that my vertical displacement is 0. So I keep putting v next to things just so that we're really, really clear. I don't do it with gravity because, with acceleration, because it's a bit more obvious. But with these ones, it's not always. So the vertical displacement is 0. It's still on that same plane. And I'm trying to solve for time. So I'm going to use S equals ut plus half at squared. So 0 is equal to 14t subtract 4.9 t squared. So I'm obviously going to solve that, solve for t, and therefore t is equal to 2.86 seconds to 3 significant figures. I believe the other answer was a negative answer. No, if I factorise it would be 0. So there you go. So that's why we only need that one answer. Finally, for this question C, find the distance OA. So we can still see the diagram. So I've changed the height of my stand that I'm putting my phone on, and I'm not quite used to how much of the page you can see. So I apologise if there's a lot of this and actually you don't need it off the page. The distance OA, so it's that distance there. So in this particular case, obviously we do have to resolve horizontally because we're finding the horizontal distance. So I know the initial horizontal velocity is 14 root 3. I know acceleration is 0. I can't use final velocity because then I've got initial and final velocity being the same. It cancels out, it means we can't solve problems. What I do know from the previous answer is time. Now obviously I'm going to use the full answer rather than the rounded answer. And I'm solving for displacement. So again, S equals ut plus half at squared. So displacement is equal to ut, so 14 root 3 multiplied by 2.857, etc. Remember, this is always going to be 0. Speed is distance times time, so we don't need to worry about the rest. So the horizontal displacement is 69.3 metres to 3 significant figures. Okay, so that's more going over the definitions. As we go on, the problems are just getting a little bit more challenging or varying in their words. So, a particle is projected from a point O with speed v metres per second and at an angle of elevation of theta, where tan theta equals 4/3. The point O is 42.5 metres above a horizontal plane. So this is a slightly more complex situation. So it's projected up there with an initial velocity of v, and if I were to draw the horizontal at that point be tan theta. Now I know tan theta is 4/3, so therefore sine theta, so opposite over the hypotenuse, our Pythagorean trivial would be 4/5 for sine, and cos theta is 3/5. It says the particle strikes the plane at point A, and this is 5 seconds after it is projected. So we know that the time from release to landing is 5 seconds, and that's really useful. And when you first read through the question, it's something that you might forget. Before we answer any problems, always going to resolve, oh dear, flinging my pen about, horizontally and vertically. So the initial horizontal velocity is v cos theta, so that's 3/5 of v, and the initial vertical velocity is v sine theta, which is 4/5 of v. Okay, so go away pen. A, show that v is equal to 20. So straight away we've got to show that question, so we do need to show all steps, which would mean if we had a quadratic to solve, we'd probably need to factorise it or use quadratic formula or something like that. So I don't have enough information to resolve horizontally. I don't know this distance yet. I don't know anything about the speeds particularly, other than it was obviously the same horizontal speed throughout, so that doesn't really help me. So there is nothing horizontally that helps me. But resolving vertically, I know a lot of information. I know that the time of flight for it to reach the horizontal was 5 seconds. I'm going to resolve upwards still, because I want my velocity to be positive, and I just find that easier personally in these situations. Even though I could do it downwards, it wouldn't really make a massive difference. So I know the time of flight is 5 seconds. I know acceleration due to gravity is negative g. I know the displacement vertically is negative 42.5. And I also know the initial velocity. So it's unusual having a component that you already fully know all 4 bits of information for. So I know the initial velocity is 4/5 of v. So SUAT, so S equals UT plus half AT squared again. So negative 42.5 is equal to 4/5 of v times 5, so that's just 4v. Subtract half times g is 4.9, so it's negative 4.9 times 5 squared. If I rearrange that, I get AT is 4v. Because I've shown all the substitution, it is enough to then skip to that step. Therefore, v is equal to 20. B, find the distance OA. So actually I need to go back to my diagram here. Now the distance OA means the literal distance between them. So what I can do is create a right angle between the vertical displacement and the horizontal displacement, which I'm going to call x. So we need to find the horizontal displacement first, so I need to resolve horizontally. So I know my initial velocity is 3/5 of v, which is 3/5 of 20, which is 12, and acceleration is 0 horizontally. I know the time taken is 5 seconds, and I'm trying to work out displacement. So S equals UT plus half AT squared, or just simply S equals UT, because we know that acceleration removes the half AT squared. So 12 times 5 is 60 metres. So therefore the distance OA is going to be the square root of the horizontal displacement squared plus the vertical displacement squared, which is 73.5 metres to 3 significant figures. So with all of these questions, it's about processing what information you have and what information you need. And that is the main difficulty with a few of these problems. Okay, example number 3. A particle is projected from a point O with speed 35 metres per second at an angle of elevation of 30 degrees. No other information given. So in terms of a sketch, really straightforward. An angle of 30. Particle moves freely under gravity. Find the length of time for which the particle is 15 metres or more above 0. So 0 is here, but obviously we're talking about 0 in terms of horizontal plane. So we want to know the length of time it's between these points, which means we need to solve at what point it actually reaches 15 metres. As ever with all these questions, I need to resolve the initial velocity horizontally, which is 35 cos 30, which is 35 root 3 over 2. And need to resolve vertically for the initial vertical velocity, which is 35 sine 30, or 17.5. Again, I have more information about the vertical movement, so I'm going to resolve vertically to solve this problem. I know my initial vertical velocity, which is 17.5. I know acceleration due to gravity is negative g. I know that the displacement I want to solve for is 15 metres vertically. So that's why I have the more information, because I know about how high it is above the ground. And I want to solve for time. s equals ut plus half at squared. So 15 is equal to 17.5 t minus 4.9 t squared. I'm going to make it quadratic. Negative 15, add 17.5 t, subtract 4.9 t squared equals 0. Put this on my calculator, and I get t is 15 over 7 seconds and 10 over 7 seconds. Obviously 15 over 7 is larger, so the time it is 15 metres or above is 15 over 7, subtract 10 over 7, which is 5 over 7, or 0.417 seconds for 3 significant figures. Really straightforward question compared to some of the others that you can get in this chapter, and actually I think compared to the first couple. These questions, quite often you just need to talk through in your head. That's what I do whenever I approach these problems. It's talking through exactly what you need and exactly what information you are given and how you can interpret the problem. Okay, example number 4. So a ball is struck by a racket at a point A, which is 2 metres above horizontal ground. Now you are actually given a diagram for this, but quite often in the exam you wouldn't. So I think it's always useful to sketch your own diagrams anyway. Immediately after being struck, the ball has velocity 5i plus 8j metres per second. So I don't actually need to worry about resolving formally. We'll talk about that in a minute though. After being struck, the ball travels freely under gravity until it strikes the ground at point B, as shown in the diagram above, but it wouldn't always be. At the moment, we haven't got an angle, theta, but actually it doesn't matter, because where I've been giving it in terms of a component vector, I know that my initial horizontal velocity is 5, and my initial vertical velocity is 8. So that is positive, I don't need to worry about those problems. Okay, so now I can start to actually approach the problem. So the greatest height, find the greatest height above the ground reached by the ball. So I'm talking about height, it's all vertical, so obviously I am resolving vertically. So initial vertical velocity is 8, acceleration due to gravity negative g. I know the final vertical velocity is 0, and I'm trying to work out displacement. Be careful with this question. The question asks for the greatest height above the ground reached by the ball. But this is going to be the displacement from the start. So that's not the greatest height above the ground. So be careful when you're actually finally answering this question. So I'm going to use v squared equals u squared plus 2as. So 0 is equal to 8 squared minus 19.6s. So 19.6s is equal to 64, so therefore s is 3.27 metres. But therefore, the greatest height is 5.27 metres, because it's the original point was 2 metres above the ground, and we want to know the whole of that height. What we have worked out is just that height. Okay, so just be careful when you're reading and approaching the question. Part B, find the speed of the ball as it reaches B. So if we are imagining the second half of my projection, so this part here, the speed is the overall part, okay? So it's not going to be specifically horizontal or vertical, it's the combination of the two. Now we know horizontal component velocity is the same as it was before. Horizontal velocity has not changed. But I don't know what the vertical velocity is here. So again, I need to resolve vertically. I'm defining down as positive because it's travelling downwards. So I'm trying to keep things sensible when I'm talking about these problems. So if I think about the whole journey, because that's all I can really do. I don't know anything else about the journey particularly. I could use from the greatest height, but I'm going to think of the journey as a whole, because I know that the overall displacement is 2 metres. I know acceleration is g. I know that the initial velocity is -8. This is where I need to be careful, because the velocity was going upwards, but I've defined downwards as being positive, so you have to be careful. And I want the final vertical velocity. So v squared equals u squared plus 2 times a times s. So v squared is equal to 103.2. So v is 10.2 to 3SF. So I want this. I want the speed. Again, I've got Pythagoras. It's the square root of 5 squared plus 10 point blah 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 squared, which is actually 103.2. So it's quite useful to have that still there, because we need the squared value. So the speed is 11.3 metres per second to 3SF. Final question. Find the angle of velocity of the ball. Find the angle the velocity of the ball makes with the ground as the ball reaches B. So we're again dealing with the same as the previous problem, where I'm trying to find this angle here. Now I know I defined theta earlier. It won't necessarily be the same theta, but it doesn't really matter because I'm now defining it for this question. So I know that the horizontal component is 5, the vertical 10.2 rounded, but what I also know is actually more accurately it's the square root of 103.2, because obviously I want my answer to be as accurate as possible. So to find theta, tan theta is the opposite, so the root of 103.2, obviously got it from this, rather than using 10.2, over 5. Therefore theta is 63.8 degrees to 3 significant figures. So these problems are more challenging. They are taking projectiles and put them into a lot more context. It's about breaking down the problem into more manageable chunks. Generally, your instinct is going to be to resolve vertically with the problem, unless what you're being asked is specifically related to the horizontal distance, or you've been given more information about the horizontal part of it. So yes, I'll set you some questions on exercise 6C before we finish projectiles when you do your next lesson with me.